are going to have our first look at a specific phenomena which is gaining importance in everyday research, that is electrowetting, and how this has led to a new branch of physics which is known as digital microfluidics. Now, the concept as electrowetting was known to us for more than 100 years, but the use of electrowetting in order to specifically move a drop of liquid from one point to another in a precisely controlled path has led to the new branch of engineering which manipulates fluid motion, and that is digital microfluidics. So, we are going to have our first look on the basics of electrowetting, its potential uses, the equations that govern the electrowetting process, the physics behind it, and how this electrowetting can be applied in a variety of fields to move liquid from one point to another. Now, whenever there is a need for precise movement of very small quantities of liquids, and those liquids could be discrete drops as well, the question comes is what would be the method, how do we move a liquid droplet from one point to another. The usual methods and machines that we know will obviously be of no use to move such a small quantity of, let us say, discrete drops. So, one has to think of alternative ways by which the drop can be made to move. One way of handling situations like this could be to alter the surface of the solid surface on which the drop is resting. Now, whenever the nature of the solid substrate is altered, it is going to give rise to a different surface energy of the system, and this difference in surface energy of the solid substrate in contact with the liquid can give rise to forces which are commonly known as surface tension forces. Now, normally what we see is that surface tension forces, they are not relevant mostly in macro scale systems, but as the system dimensions grow smaller and smaller, the effect of body and other forces would progressively diminish, and the surface forces would take over, and they could be the major force applicable when the system dimension becomes millimeter level, and even more prominent when it becomes at the micron level. So, the basic problem boils down to how do we change the surface energy of a surface, and if we can change the surface energy of the surface, would that lead to a motion in the droplet. So, we need to apply certain external forces maybe, or certain operations need to be done on the solid surface to change its surface energy. So, initially in the first part of this lecture on electrowetting, we would concentrate on the ways to change the surface energy and thereby the surface tension of the system. So, as I mentioned that the driving forces become different when we go into the micro scale system, and compared to macro scale, surface tension starts to dominate as the surface to volume ratio increases and in the micro scale. So, can we use surface tension for the precise manipulation of droplet in the micrometer scale? So, this is a fundamental question or the fundamental process which then has led to 4 distinctly different fluidic operations. Can we use surface tension as a force to create a droplet or to transport a droplet from one point to another? Can we cut a droplet into a number of smaller droplets, and can we merge 2 droplets together to form a relatively bigger droplet? Because these are going to be fundamental operations which would be necessary, which would convert the droplet based fluidic systems to digitize them in such a way, and this has given rise to a new microfluidics paradigm that is commonly known as digital microfluidics. So, in this class we will see what digital microfluidics is all about, and the forces, the science and the engineering applications of digital microfluidics. So, this has given rise to the first thing is can we change the surface energy. Now, towards the middle of this lecture, I will give you some examples of changing the surface energy of a surface by external means, which which are may not be reversible, which are difficult to maintain. So, the need to have something which is quote unquote switchable is extremely important. Can we think of a system in which the nature of the surface changes very quickly to something that drastically different? For example, from hydrophobic, can we make the surface hydrophilic, and then when that external effect is taken out of the system, it immediately goes back to its previous state which is hydrophobic. So, electric field has been shown to alter the surface energy in such a way that this hydrophobic hydrophilic interaction or interchange is easy to accomplish. The first example of this electric double, the first example of electric field enhanced wetting that can be encountered in a droplet was given by the scientist Lippmann around 1875. The example that I am showing here, the figure that I am showing here is, let us say this is a liquid which forms a finite contact angle, a large contact angle with the solid which is a conductor. So, this is a conductor and we have an electrolyte in contact with the conductor, and a finite large contact angle is formed in between the solid liquid interface, and then a potential difference is applied in between the electrode and the electrolyte. Now, when that happens, the electric double layer is formed in which the charges, opposite charges are going to accumulate at the solid side of the solid liquid interface and on the liquid side. So, if we can the electric double layer can be thought of, let us say this is a solid, this is which is the where, and we would like to see how the electric double layer is going to be formed, and this is in contact with a battery, and here I have an electrolyte. So, when the circuit is on, what we are going to see is that positive charges are going to accumulate on the solid side of the interface, and the negative charges from the electrolyte will form a layer in the electrolyte. So, this formation of oppositely charges near the solid liquid interface on application of an electric field is the thickness of this is known as the double layer. So, we would say that as double layer has formed inside the electrolyte on very close to the solid liquid interface, and when that happens, this accumulation of charges, since it is a spontaneous process, it is going to lower the energy of this surface. As the surface energy is lowered, the solid liquid surface energy is lowered, this will give rise to spreading of the electrolyte on the solid. So, this phenomena or this concept has been utilized for electrowetting. So, if I have a droplet which is sitting on a solid, and then I have an electric field being applied between the liquid of the droplet and this being the conductor. So, what would happen is that the charges are going to form near the interface inside the droplet, and positive charges are going to accumulate on the solid side of the interface. As a result, the surface energy will change and the droplet will spread. So, this spreading of the liquid present in the droplet on application of an electric field is known as electrowetting, which was first observed by the scientist Lippmann somewhere around 1870s or so. So, can we now this, since this was known for quite some time, but can we use this for some practical applications? That is something which you would like to see. But if you see this entire process, you would see that there is a limitation, because if the potential difference between the solid, the electrode and the electrolyte is slightly large, I mean if it is only if it is very small, then this electrowetting phenomena can be observed. But if you would like to increase the voltage, then this process will break down, since a current would flow in between from the electrode to the electrolyte. So, only few tenths of volts can be applied in between the electrolyte and the electrode without passing a current in between them. So, how do we? So, this limits severely limits the applicability of electrowetting in terms of changes in contact angle, in terms of appreciable changes in contact angle. So, we can only change the contact angle by a small amount, because any increase in voltage would lead to a current flowing in between the solid and the electrolyte, thereby rendering the entire electrowetting process inoperable. So, in order to circumvent this specific problem, the concept has come later on, is if we could introduce a dielectric layer in between the electrode and the droplet, then the question of having a current passing through in between the solid and the electrolyte at slightly higher voltages can be eliminated. So, that is the concept which has been shown here, and which is commonly known as the electrowetting on dielectric. So, in electrowetting on dielectric, a dielectric layer is placed in between the electrode and the liquid. So, the liquid would be here, which is not in contact with the electrode anymore, but a dielectric layer will be introduced in between the two. So, now I can have appreciably sufficiently higher voltages that can be applied in between the electrode and the liquid. So, the electric field is large, and as the electric field is large, significant changes in contact angle would be possible, and this is what is shown in this figure, which is taken from a publication by Lee in 2002, which has appeared in the journal Sensors and Actuators. Here now I have the solid covered with a dielectric coating, and it is in contact with an aqueous liquid. So, when this circuit is closed, that is not going to be formed any electric double layer, but the change in energy takes place in the hydrophobic dielectric layer. So, the nature of this dielectric layer has to be hydrophobic, and since it's hydrophobic, the liquid is going to form a convex meniscus over here. Now, when you apply sufficiently high electric field in between this and the liquid, then the dielectric layer acts as an insulator, but and so there is not going to be formation of any electric double layer, but the change in energy, surface energy of the dielectric will cause a change in contact angle. So, you can see that from an almost completely non-wetting system, it has become partially wetting system with a distinct change in the curvature. So, if let us say this is mercury and mercury, then you could see that the convex meniscus has been depressed and it has become a concave meniscus. So, this depression and change in shape of the liquid mercury meniscus can be monitored as a function of applied voltage, and you would see that it is going to follow a certain law, certain role, which we will see subsequently. But here you can see that a hydrophobic surface giving rise to a retracting meniscus can be changed to an hydrophilic substance giving rise to an advancing meniscus by simple application of an externally applied electric field, which has a number of advantages that I will list subsequently. Now, a digital microfluidic system can be of two different can be of fundamentally two different technologies. One is an open system and the other is a confined system. So, when we are dealing with just a drop on a surface, okay, and this is an example of an open system, whereas if I have a plug of liquid in another medium, and this is the electrode and this being the dielectric, then it is an example of a closed system. So, in digital microfluidics or in electrowetting, we would see applications of both an open system or an closed system, and with fundamental advantages. So, let us try to see what are the advantages of digital microfluidics. Now, let us say you have a reaction which is taking place inside a droplet. Now, since the size of the droplet is extremely small, the resistances to mass transfer, the diffusion length, the diffusional resistances to mass transfer would be minimized to a large extent inside a droplet. So, if you have a reactant droplet, reactant 1 droplet and reactant 2 droplet, you could bring them close together, you could merge them and you can form a larger droplet. Now, inside the larger droplet, still it is very small in size, if it is of microliter dimensions, the resistance to mass transfer would be so small that the kinetics of the reaction can be made faster. So, any reaction which is mass transfer limited would be ideally suited for operation inside a micro droplet. And you could design your system in such a way that you start with a large droplet. Okay. That large droplet could be split into a number of smaller droplets using a specific microfluidic operation. Then each of these smaller droplets can be made to move in a path separate from each other. Now, on the path sits something which is going to react with the droplet which is coming in that path, and when that reaction takes place, suppose you can monitor the reaction from outside, then a specific, let us say, chemical present in the micro droplet can be monitored, or its concentration can be measured. So, in this way, depending on how many droplets you are dealing with, how many droplets you have broken the initial droplet, you could have several chemicals which can be characterized by reacting them with different chemicals, different reagents. So, this has very important application in many diagnostic devices or lab on a chip diagnostic devices, where one drop of blood could be split into a large could be to a significant number of micro droplets, and any specific chemical of interest can be measured into that micro droplet by making it react with some known reagent. So, one droplet could be used for blood sugar monitoring, the other could be for blood urea monitoring, and so on. So, the compartmentalization of reactions in small droplets giving rise to larger rate is one big advantage of this entire process. So, what you can see that this in turn would reduce the amount of reagent necessary for such an operation, and this kind of process can also enhance and accelerate chemical and biochemical screening processes, crystallization of certain proteins, the kinetics of enzymes, and so on. So, this definitely has significant application, and when we think of applying these concept of electrowetting to specific applications, for example, lab on a chip, we need to take care of, or we need to address certain issues, like what are the fundamental and applied aspects of electrowetting, what kind of basic equation, governing equation can be used, can be developed for electrowetting. So, what are the origin of electrostatic forces that can change that can change contact angle, or that can induce both contact angle and motion for the entire droplet? Is there any limitation of this electrowetting equation? So, in other words, we would like to address, we would like to identify the failure of the electrowetting equation, which is known as the saturation of the contact angle at high voltages. Apparently, it seems that as voltage increases, as the applied field is increasing, the contact angle will become smaller and smaller. But is there any limit to it? We would see that beyond a certain voltage, the contact angle becomes independent of the applied voltage. So, no matter, even if you increase the voltage beyond that point, beyond that value, the contact angle will not decrease anymore. So, your ability to induce a change in contact angle would not follow the basic governing equation or our idea that by increasing the value of the value of the applied voltage, we could reduce the contact angle to any value that we desire. In other words, it is shown experimentally that you can never make a partially wetting system or a non-wetting system convert to a completely wetting system. So, you would never be able to achieve zero contact angle. So, this saturation of contact angle with respect to the applied voltage is one limitation that we have to keep in mind. And then we have to also think about what is the dynamics of electrowetting. Okay? How do we make a droplet move from one point to another? What are the factors that are going to govern the process, the speed of the process, the response of the electrowetting phenomena as the droplet size is changed, the velocity with which the droplet would move. So, what are the design parameters that we can change to make the droplet move with a constant velocity, with some velocity that we would like to have? And then finally, I would give an overview of the many exciting commercial applications or upcoming commercial applications of the electrowetting concept. So, I would concentrate mostly on electrowetting on dielectrics, which is which in the short form is commonly known as EWOD. So, we will see, we will go into the depth of EWOD in this class and in the next class as well. Okay. We all know that the important consequence of miniaturization is the rapid increase in the ratio of surface to volume ratio. Now, one of the major focus of research for a very long time is how do we control surface energy and the surface forces. When the system size becomes smaller, we know that the capillary forces would dominate. So, which is a function of the surface tension. So, how do we change the surface tension? So, before the concept of electrowetting was utilized to change the surface energy, so there are several attempts to change the surface tension. So, ways to influence the interfaces. One can use a temperature gradient to make a change in the surface energy. What we know is that surface tension is a strong function of temperature. So, if you can have a difference in temperature in between 2 points on the surface, then the surface tension values at these 2 points would be different. Now, we are therefore creating a surface tension gradient on the surface. So, just like pressure gradient that is imposed from outside, here through a temperature gradient, we are imposing a surface tension gradient that can be used to make liquid flow, to make a fluid flow from one point to another. So, this temperature dependent motion of liquid, which is due to surface tension gradient, is known as Marangoni flow. Now, this Marangoni flow can be affected by surface tension gradient, by the imposition of a temperature gradient, or by the imposition of concentration gradient as well. So, if we can have a solution containing a solute, and if the solute concentration at 2 points are different, then what would happen is that this would create a surface tension gradient, and then this would give rise to flow. So, we can have Marangoni flow, a surface tension gradient driven flow caused by either a temperature gradient or a concentration gradient. So, this has been shown to become important when the system size becomes smaller as the surface forces start to predominate over all other forces. Now, this has been there has been some effort in order to use this for movement of fluid, but there are certain problems associated with it. In order for a droplet to move on account of induced temperature gradient, the value of the induced temperature gradient has to be very large. So, which is impractical in most of the cases to be used for practical applications. You need several tens of or maybe hundreds of degree centigrade per millimeter in order to cause a liquid droplet to move on account of surface tension gradient. Similarly, how do you practically create a concentration gradient over over a very small distance? Okay. So, this has given rise to secondary flows which people have encountered, but these cannot be the primary ways to move liquid. Now, there has also been efforts to make a topographical structuring of the surface or chemical modification of the surface, which would give rise to local wettability gradient. So, there has been a report in which you can have alternative, you can have a gradient of wettability which is thrust upon the surface. You could create a wettability gradient on a surface by chemical means, by the deposition of certain chemicals on a silicon wafer, for example. There is a specific chemical which, when deposited by a vapor deposition process on the silicon wafer, silicon substrate, it would give rise to a wettability gradient. And you could show, it has been shown that a droplet will move in the direction of enhanced hydrophilicity even against gravity. In other words, if you have an inclined surface and if you put a drop of liquid on the higher hydrophobic side of the substrate, then that droplet will move against gravity along the substrate. So, which is very obvious, because the effect of gravity becomes unimportant as the system size becomes smaller. So, the gravity is no longer important. So, even if the substrate is at an angle inclined, the droplet, due to the hydrophobicity gradient, it will move from the hydrophobic to the hydrophilic side, which is extremely interesting to see. Okay. It defies the logic, and you would see a droplet moving along the incline, moving up the incline. Now, there are certain disadvantages of these chemical and topographical patterns is that they are static in nature. Once you modify the chemical nature of the surface, it is going to remain that way. So, there is no way by which you can switch it on and off. Okay. So, they are static in nature, and therefore, you cannot effectively control or effectively use the same surface for a different application. Okay. Once you make the surface will remain the way throughout the operation, and there are obviously fabrication of such surfaces will be more complex, and mostly this would give rise to secondary flows and not primary flows. So, we are still looking for a switchable method of changing the nature of the surface, which is reproducible, which is easy to make, and which would give rise to sufficient force for the effective movement of droplets. And this has given rise to the concept of, or to the application of, electric field to change the nature of the surface. Now, so therefore, electrowetting has proven to be extremely successful. You can change contact angles by tens of degrees, 20, 30, 50 degree change in contact angle is also possible, and switching speeds are much more than compared to the other cases. Mostly the switching speed is going to be governed or controlled or limited by the hydrodynamics of the droplet. How would the droplet respond to the application of electric field? How fast would be the response, and the response would depend on mostly on the viscous forces. May not be on the inertia, but it is a viscous force which is going to dominate what would be the frequency with which, or what would be the response frequency of a droplet with change in potential difference across the surface. But still the switching speed is much more than that of the other processes we have described so far, and this is extremely important for commercial application, the stability of the surface without any noticeable degradation. So, as long as we have a very stable surface which is reproducible and where you do not see much degradation over repeated use, that with a reasonable switching speed. So, this essentially tells us that electrowetting will definitely be the method of choice for such operations. And we see nowadays that droplets are moved freely along the programmable path. So, you are going to have a large number of electrodes in probably in an array like this, where on the surface you have several electrodes, and depending on how you switch these off and on, a droplet sitting over here can be made to move either in direction or it can take any path it wants. I mean, you can program the switching on and off these electrodes and thereby make the droplet move on any prescribed path, thereby creating enough flexibility in the entire design of the process such that it can be split, and one droplet will move in this direction and the other droplet will move in another direction. So, you can have reagents parked on one of the electrodes over here and another electrode over here, and you can monitor the some property, it could be fluorescence, some property of the droplet when it reacts with the reagent present in this electrode and present in the other electrode. Thereby, you could monitor maybe the concentration of two species present in this droplet. So, the programmability, the easy programmability of the entire matrix, electrode matrix, two dimensional electrode matrix gives enough flexibility of the system which has lot of potential for their subsequent commercial use. Now, this is a classical setup, figure of a setup, where in 1875 Lippmann has shown that there is sufficient or considerable depression of mercury when in contact with an electrolyte solution, and you can vary that depression of mercury meniscus by applying a voltage between the mercury and the electrolyte. But as I said, it is limited by the application of a very small amount of very small quantity of voltages. So, in the early 1990s, Burge has introduced the idea that a thin insulating layer can be placed in between the conductive liquid and the metallic electrode to eliminate the requirement of a very low voltage, to eliminate the possibility of electrolysis, and this has given rise to electrowetting, the new concept electrowetting on dielectric, or in simply EWOD. So, if you look at the basic aspects of electrowetting, one is we are dealing with droplets. The sizes are about a millimeter or it could be less, and they are going to be of partially wetting liquids on solid substrates. The solid substrate could be a silicon wafer, and the entire process is going to be governed by the bond number, which is defined as g, the acceleration due to gravity, the change in density, the difference in density, the radius of the droplet, and sigma LV is the surface tension. So, the bond number essentially gives us the relative strength of gravity with respect to surface tension. So, since the effect, if for these electrowetting, the effect of surface tension because of the size of the system overshadows the effect of gravity, and the bond number is smaller than unity. So, since the bond number, if the bond number is less than unity, then the effect of gravity can be neglected and the behavior of the droplet is determined by surface tension alone. So, now we would like to take a look at the different forces which are present in a droplet and what would be the governing equation for free energy, for energy of a droplet when it is at equilibrium. So, the free energy of a droplet is a function is a function of the different interfacial energies of the solid liquid interface, of the solid vapor interface and the liquid vapor interface. So, if this is the contact angle, then we know that at steady state the sum of the free energy of a droplet is going to be the sum of the areas of the interfaces weighted by their respective interfacial energies. For example, sigma L S V solid vapor, solid vapor, solid liquid and the liquid vapor. So, at stage that in the equation that governs the free energy is this, where lambda is equal to the pressure drop across the liquid vapor interface. So, if you minimize this equation, this would lead to two very well known equations, well known conditions that the equilibrium morphology of the droplet must fulfill. One is the very famous Laplace equation, which tells us the pressure jump at the across the liquid vapor interface. So, delta P L V is going to be equal to sigma L V, that is the surface tension, liquid vapor surface tension, and K, where K is the curvature of the drop. So, the curvature of the drop is nothing but the inverse of these radii of curvatures. And the second equation is Young equation, which gives us the value of the equilibrium contact angle as a function of the solid vapor surface tension, the solid liquid and the liquid vapor surface tension. Now, one must emphasize at this point is that both of these equations are approximations and they are valid only when the sizes are in mesoscopic scale. When the system size becomes smaller and smaller, this type of equations may not be valid. For example, if we think of when a liquid meets a solid, as the thickness becomes smaller and smaller, let us say when the size is less than 0.1 micron, or more specifically when it is of the order of 500 angstrom, near the point where the liquid is in close proximity with the solid, additional forces apart from this sigma k, that is delta P is equal to sigma k. This is the surface tension, liquid vapor surface tension, and K is the curvature. But beyond this, when the size of the film really becomes very small, additional forces such as intermolecular forces of attraction starts to become important in this range. So, if I magnify this area, we would see for a partially weighting system, it is going to be like this. So, there would be an adsorbed flat film ahead of the meniscus and a transition region. So, in this region the intermolecular force would be important. In this region both intermolecular and surface forces would be important, and in this range is going to be controlled totally by surface forces denoted by sigma k. So, the equations, the two equations that we have seen so far, we have seen the Young's equation and Laplace equation are valid for the mesoscopic scale. We must understand, we must underline the fact is that these two equations will require presence of additional terms when we are dealing with the really thin microscopic level, microscopic contact angles or the contact line in these cases. So, we with this limitation in mind, now we move to our next part, which is how do we express the, or what is the electrowetting theory for homogeneous substrates. And we have two different approaches, one is the thermodynamic approach and the other is the electrochemical approach, and it is basically between a metal electrolyte interface. And when you apply any voltage, as I have mentioned, a double layer is going to build up spontaneously at the solid liquid interface, and it consists of, let us say, positive charges on the solid side and negative charges on the liquid side. So, this presence of double layer, the formation of double layer is a spontaneous process. Since it is a spontaneous process, this spontaneous process must give rise to a change, a decrease in the gives free energy of the system. So, the change in free energy is going to manifest itself by a change in the effective interfacial tension, which is connected with the surface charge density, and U is the applied voltage. So, the change in surface tension, interfacial tension, is going to be a function of the applied voltage, and it is also going to depend on the surface charge density of the counter ions. So, with these, now we can move to the next assumption, which is like how would the charges are distributed in the liquid. Okay. Obviously, the concentration of the charges very near to the solid surface is going to be more, and as we move away from the surface, the concentration of the counter ions will reduce progressively. In fact, it would reduce drastically. So, what kind of distribution of counter ions should one take when one goes from a solid liquid interface and into the liquid? Now, this is difficult to handle in a compact form. So, the concept or the proposal of Helmholtz, the model proposed by Helmholtz is used, which assumes that all the counter ions are going to be situated in a very thin layer of the order of few nanometers, and this Helmholtz model for the electric double layer has given rise to the concept of a double layer with a fixed capacitance per unit area. So, here epsilon 1 is the dielectric constant of the liquid, and dH is the thickness of the layer as proposed by Helmholtz model. That is, it's all the charges, all the counter ions are going to be located at a fixed distance from the surface. So, when you use this and integrate this the previous equation, this has given rise to the change in surface energy as a function of, on application of some voltage U, as a function of the surface energy when you do not have any electric field, and these are properties of the solid liquid interface. This is the applied voltage, this is the thickness as predicted by Helmholtz layer, and UPZC is the potential difference of zero charge. And this, the introduction of UPZC is important because mercury and many other surfaces acquire a spontaneous charge when they are immersed into an electric solution even at zero voltage. So, in order to overcome that potential, some excess external potential has to be applied in order to make the surface truly zero charge. So, PZC is that charge which has to be applied in order to make this compensate for this accumulated potential difference or the generated potential difference even at zero charge. So, this equation now can be inserted into Young's equation, where the cos theta, theta being the contact angle at any given voltage, can be related to the equilibrium contact angle, and in terms of system parameters such as the property epsilon 1 dH, sigma LV is the surface tension at the liquid vapor interface, U is the applied voltage, and PZC, as I mentioned, is the potential at zero case. So, for typical, if you take typical values of dH, epsilon and sigma LV, let us say for a water, this ratio of the right hand side of the equation, this entire ratio is of the order of 1 volt to the power minus 2. Now, you can see that with application of voltage, this increases rapidly. So, the contact angle would increase rapidly upon application of a small voltage. Okay. So, but the limitation is you really have to operate it below the onset of electrolytic process. So, therefore, it can only be operated up to a fraction of millivolts. So, if your potential difference is beyond that fraction of millivolts, then your electrolysis process would start, and the entire process will be unusable, entire process will break down. So, even though it is a very interesting phenomena to look at very low there the fact that it can only be used at a very low value of the applied potential limits its use for any practical applications. So, simple electrowetting will be difficult to implement for any practical application. So, one has to then go to the application or go to the introduction of an dielectric in between the electrolyte and the electrode, which would make the electrolysis impossible at elevated voltages as well. So, that is what we are going to look at next. So, a thin dielectric film insulates the droplet from the electrode, and the electric double layer builds up at the insulator droplet interface, thereby causing a change in the surface energy of the dielectric, and the capacitance, since the insulator thickness d is much larger of the order of microns compared to dh, which is of the order of nanometers, then the capacitance of the system is reduced to a large extent, and this is the capacitance of the insulator, where this is the epsilon d stands for the dielectric, and one has to see that this d is the thickness of the dielectric, and since the capacitance is so different, then the entire capacitance of the system can be approximated as if it is the capacitance of the dielectric. So, in the previous expression therefore, is modified by introducing only sigma d in here, d being the thickness of the dielectric, and the value of UPZC is so small that for EWOD cases, where the applied voltages would be in the order of maybe 50, 100, 200 or 300 volts, the value of PZC would be unimportant, and that is why it has been dropped from the equation. So, the compact equation for EWOD is the change in the effective surface energy of the system on application of an potential is going to be equal to whatever be the potential, whatever be the surface energy at 0 voltage minus this factor. And in this equation, the entire dielectric layer is therefore considered part of one effective solid liquid interface, and with thickness of the order of 1 micron compared to the electric double layer, which is of the thickness of few nanometers. Now, when you plug that into Young's equation, this has given rise to the famous equation over here for EWOD. Contact angle equilibrium contact angle is equal to the equilibrium contact angle plus this term multiplied by u square. This eta is known as the dimensionless electrostatic number, which measures the strength of the electrostatic energy compared to the surface tension. So, this is basically something on which you can control, which you can design by changing the thickness of the dielectric layer, or by changing the material and by changing the potential, applied potential. You can have a different rate or different value for the new contact angle on application of voltage. Okay. So, this essentially depends on the properties of the insulating layer and on the thickness of the insulating layer. So, this number for EWOD is smaller, much smaller than the number corresponding to electrowetting, because of this dH over here and D over here. So, this means that the voltage required to achieve a substantial contact angle decrease in EWOD is much higher. That means, if you would like to change the contact angle by let us say 5 degree, the amount of potential difference that you have to apply would be of the order of 1/10 of a millivolt, let us say 1/10 of a millivolt in simple electrowetting. But in order to obtain the same 10 degree change in electrowetting on dielectric, the applied potential would probably be about 50 degree or maybe even more. So, you require higher voltages to actuate contact angle changes in electrowetting on dielectric. However, the major advantage is that Now, you are not restricted to few millivolts, you can go to 500 volts. You are only limited by the fact that at very high elevated voltage there could be current passing through the dielectrode, which would result in a phenomena known as dielectric breakdown. So, when the dielectric breakdown takes place, the entire surface becomes unusable, and this is some sort of a limitation of the EWOD, but it still gives us tremendous flexibility in terms of affecting a major change in the contact angle, which would be subsequently very important for the dynamics of the droplet on a surface. So, EWOD is the preferred method over EW, and this is an example of the contact angle saturation, where we could see that the parabolic nature of cos theta variation with the potential is more or less valid up to, let us say, about 300 volt. But beyond 300 volt, even with increase in the potential, this becomes more or less relatively it's free of, I mean, it's not going to it's not going to be a function of u anymore. So, this contact angle saturation at somewhere around this value is another limitation of EWOD. So, if this is known as the contact angle saturation, and you obviously cannot work beyond the value, and but even then this would probably be a change in contact angle by about 30 degree, 50 degree, that is possible. But you cannot make a non-weighting system completely weighting by simply keep on increasing the potential difference. So, you are either going to be limited by the dielectric breakdown, which is essentially passing of a current through the dielectric at higher voltages, rendering the surface unusable for subsequent use, or you are going to hate the contact angle saturation phenomena, and you would not be able to go beyond that. So, that is what I have already said, that you get some expression, but a saturation value between 30 to 80 depending on the surface, depending on the system, you are going to the phenomena of contact angle saturation is still not well understood. Now, in the next class we are going to talk more about the complex surfaces and droplet morphologies. Now, how we can change, how you can make a transition from a hydrophobic surface to a hydrophilic surface by imparting certain structures on the surface. And if we have substructures on the surface, microscopic level structures on the surface, how that change the weighting nature, and how they can be integrated with EWOD to have smoother motion of the droplets, for example, over a surface. And we would also concentrate on the dynamics of the electrowetting process, the factors on which this electrowetting process would depend, in how or what are the interesting and important applications of EWOD for our everyday use. So, that is all for today. Thank you.